Let's talk about, so we talked about OR. OR is pretty straightforward. It's actually, OR is an intersection, for what it's worth. OR is, we're adding probabilities together, as you saw here, but with the threat of double counting. So we can add probabilities together. That is great, but here, for instance, we had added together, I know I've got a little bit of multiplication right there, but for instance, we had added up the odds. We had 1, 2, 3, 4, 5, 5 times 4. We had 20 odds plus 12 faces, and that's where 32 would come from. Okay? Or is addition with watching out for overlap. Well, that makes and multiplication. You see, when things happen together for independent events, and we'll talk about dependent in a minute, it's the probability of A and B happening is the probability of A happening times the probability of B happening. Okay? Some of your simplest situations are, well, let's talk about this bag of marbles here, okay? Now again, independent is an important word here, but still reviews, I'm not going to spend tons of time on it. Events are independent if one event does not impact the other. You know, gambler's fallacy, a problem that people have sometimes with gambling, they don't understand that events are independent. You know, if you're pulling an arm on a slot machine and you put $1,000 into it, it doesn't make the next pull any more likely to win, even if you've been losing all of this time. If you play the lottery for 10 years every single week and you never win, you're not due for a win. You're not more likely to win the next ticket you buy. Don't fall victim to that. Okay? Every lottery ticket is an independent event. Okay? You're not improving your probability here. Okay, moving on. Bag A contains 9 red and 3 green marbles. Bag B contains 9 black and 6 orange. So what's the probability of picking 1 green and 1 black? Okay, well, this is very straightforward and something that you should be very familiar with. You would simply take the probability of A and the probability of B happening separately. What's the probability of choosing a green marble from bag A? Well, it is the elements I'm interested in divided by the total number of elements. So there are 12 marbles in bag A, so it's 3 out of 12. Okay. Probability of picking out a black marble from bag B, well, let's see. There's 9 elements I'm interested in out of a total of 9 plus 6, which is 15 marbles. Multiply those together. Oh, you know what I'm going to do? I'm going to simplify this first. Seems easier. 1/4 times, divide by 3, 3/5. Oh, that's easier. 3/20. Of course, if you multiplied these out, you'd have also gotten something that would have reduced to being 3/20. Okay? Simple, right? Let's talk about more bags. So here's a couple bags. Let's talk about the difference between replacement and non-replacement. So thus, we're suddenly getting into non-independent events. So A here, and that key word, replace, is huge. A represents independent events, or two independent events. A bag contains 9 red and 3 green. There's our same bag. 2 draws, probability of sending a red marble, and there's that word, a green marble. So a red marble has a 9 out of 12 chance. Then you put the marble back, because you're a nice guy, I guess. The green marble has a 3 out of 12 chance. So to do this in this order, you multiply across the board, you get 27 over 144. I'm not crazy about that number. If we reduce it, well, you know what? I'm going to reduce it on this side first. Let's instead call this 3/4 times 1/4. 316 is much nicer. I like that a lot. What if the marble is not replaced? Okay, well, you've done these problems before. You've seen this. Okay, it changes the probability. It is no longer P of A times P of B. I mean, P of A. Essentially, what I'm trying to say is P of A and B is not going to be P of A times P of B. Instead, we get something more complicated. P of A times P of B given A. And we're going to talk about given here in just a minute. Okay, we're talking about, it's called a conditional probability. So let's actually analyze this. I'm taking this from the other direction that I usually do, but I think this is going to be good for us. Okay, so we're still doing a multiplication problem. We're still going to deal with P of A. Again, this is for well, you know what? We'll call it non-independent. Let's just call it dependent events. Okay, it is not P of A times P of B. It is P of A times P of B given A. So let's talk that through. So first marble is not replaced. So P of A, good news, that part doesn't change. What is the probability of, what was our first marble? Pulling out a red? Right, so what's the probability of pulling out a red marble? It is 9 out of 12. Easy. Easy. What's the probability of pulling a green marble given, that's an important word that I'm going to emphasize here on the next couple of slides here. What's the probability of pulling out a green marble given that your first one was red and you didn't put it back? Okay, well, so we pocketed our red marble. How many marbles are left in the bag now? Well, now there's only 11 marbles left in the bag, and how many of them are green? Well, there's the good news. None of the greens changed. So it's still 3. There's still 3 green marbles, but there's 1 fewer marble. We do this multiplication, we get 27 over 121. Wait, oh, sorry, no, that's 11 times 11. My mistake, that's 132. Don't listen to me. This still simplifies, but not near as much as the other one did. I believe you're going to get 12 over 44, if I'm not crazy. Yeah, because you still get 3/4. Oops, so it was 9. See, look at that. You shouldn't do this in your head. It's a bad idea. You get 9 over 44. Okay. Awesome.